This is SpaceTime Series 21, Episode 68, coming up on SpaceTime. It seems those strange auroral streams, collectively known as Steve, are not auroral after all. Solving the mystery of Jupiter's colourful cloud bands, and launch of the Aeolus wind satellite. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study claims that strange auroral streams, collectively known as Steve, are not auroral after all, but an entirely new celestial phenomenon. The mysterious thin ribbons of purple and white light that sometimes appear in the night skies were first brought to the world's attention in 2016. Amateur photographers have been capturing the phenomenon, colloquially known as Steve, on film for decades, but the scientific community only got wind of Steve in 2016. When scientists first looked at images of Steve, they realized the lights were slightly different from that of typical aurora, but they weren't sure what underlying mechanism was causing it. Now, a new study in the journal Geophysical Research Letters reports on researchers analysing a Steve event from March 2008 to see whether it was produced in a similar manner to aurora. Aurora occur when high-energy charged particles, usually protons and electrons generated during geomagnetic storms on the Sun, collide with Earth's magnetosphere and are guided by the planet's magnetic field lines through the ionosphere, a region of charged particles. As these particles travel towards the north and south magnetic poles, they collide with oxygen and nitrogen atoms and molecules in Earth's upper atmosphere, causing them to excite and emit photons, giving off a glow and producing the colourful curtain-like displays known as the northern and southern lights, the Aurora Borealis and Aurora Australis. The colours being emitted during aurora depend on the particles being ionised. Reddish-brown glows are caused by collisions of particles with single oxygen atoms in Earth's upper atmosphere, usually above 300 kilometres. Lower down, the more common green hue is created by single oxygen atoms down to altitudes of around 100 kilometres. The kaleidoscopic curtains suddenly turn a whitish-yellow beige when nitrogen's mixed in with the oxygen. And aurora can also exhibit blue, red and even purple glows in lower atmosphere caused by the excitation of molecular nitrogen below 100 kilometres. But this new study suggests Steve is produced by an entirely different atmospheric process than the aurora, making it an entirely new type of optical phenomenon. The study's lead author, B. Gallardo Lacourt from the University of Calgary, says right now science still knows very little about Steve. The author suggests Steve is a kind of air glow, a glowing light in the night sky that's distinct from aurora. Studying Steve will help researchers better understand the upper atmosphere and the processes generating light in the sky. A group of amateur auroral photographers first brought Steve to science's attention in 2016. A Facebook ground called the Alberta Aurora Chasers had occasionally noticed bright, thin streams of white and purple light running east to west in the Canadian night sky when they were photographing aurora. While aurora can be visible every night if the viewing conditions are right, the thin light ribbons of Steve were only visible a few times a year. And light from Steve was also showing up closer to the equator than aurora, which can usually only be seen at higher latitudes. Photographers first thought the light ribbons were created by excited protons. The problem is, protons can only be photographed with special equipment. That's because the light that protons produce usually falls out of the range of wavelengths picked up by normal cameras. Looking for a name for their phenomena, the Aurora Chasers eventually dubbed the light ribbon occurrences Steve, in a reference to the 2006 film Over the Hedge. When researchers presented their data about the unusual lights to a 2016 scientific conference, a fellow space physicist proposed converting the name to the backronym, yes I did say backronym rather than acronym, to the backronym STEVE, which in this case stands for Strong Thermal Emission Velocity Enhancement, and the broader scientific community adopted it. Scientists then started using data from satellites and images from ground-based observatories to try and understand what was causing the unusual light streaks. The first scientific study published on Steve identified a stream of fast-moving ions and superhot electrons passing through the ionosphere right where Steve was being observed. The researchers suspected that these particles were connected to Steve somehow, but were unsure as to whether they were actually responsible for producing it. After that first study, in which Gallardo Lecourt was one of the co-authors, the researchers wanted to find out if Steve's light was being produced by particles raining down into the ionosphere, as typically happens with aurorae, or whether there was some other process at work. In this new study, Gallardo Lecourt and colleagues analysed the Steve event, which occurred over eastern Canada on March 28, 2008, using images from ground-based cameras that record auroral activity over North America. They coupled the images with data from NOAA's Polar Orbiting Environmental Satellite 17, which luckily happened to be passing directly over the ground-based cameras during the Steve event. This satellite's equipped with an instrument that can measure charged particles precipitating into the ionosphere. The study's results suggest that Steve is in fact an entirely new phenomenon, distinct from typical auroras. The satellite detected no charged particles raining down into the ionosphere during the Steve event, meaning it's most likely produced by an entirely different and as yet unknown mechanism. The author's next step will be to determine whether the streams of fast ions and hot electrons in the ionosphere are creating Steve's light, or if the light's actually produced higher up in the atmosphere. We'll keep you informed. You're listening to SpaceTime. I'm Stuart Gary. Jupiter is the largest planet in our solar system, and unlike the Earth, Jupiter, a gas giant, has no solid surface, instead comprising mostly of hydrogen and helium. However, there are several strong jet streams flowing west to east in Jupiter's atmosphere that are in many ways very similar to Earth's own jet streams. Clouds of ammonia in Jupiter's outer atmosphere are carried along by these jet streams, forming the planet's distinctive white, red, orange, brown and yellow cloud bands. Scientists know a lot about jet streams in Earth's atmosphere and the key role they play in weather and climate, but researchers still have a lot to learn about Jupiter's atmosphere. The findings, reported in the Astrophysical Journal, are based on computer simulations looking at the interaction between atmospheres and magnetic fields. Previous simulations had suggested that jet streams were suppressed into zonal flows by strong magnetic fields. Zonal flows are ubiquitous in rotating systems. Prominent examples include Earth's polar and subtropical jet streams in the atmosphere, the Antarctic circumpolar current in the ocean, the winds in Jupiter's atmosphere, and flows in the atmospheres of Saturn, Uranus and Neptune. Astronomers have long debated how deep jet streams can reach beneath the Jovian cloud tops. It's known that zonal flows have an indirect effect on the gravitational field of Jupiter. And so, detailed measurements of the Jovian gravitational field by NASA's Juno spacecraft has allowed astronomers to infer that these jet streams can reach as much as 3,000 kilometres below the Jovian clouds. One of the study's authors, Dr. Navid Constantino from the Australian National University, says until recently little was known about what happened below the Jovian cloud tops. The authors used mathematical calculations for the instability that leads to jet streams when magnetic fields are present, together with new work comparing theoretical predictions with results from previous computer simulations. Combined, the new research has provided a mechanism for trying to explain how magnetic fields suppress zonal flows. The study shows that with the magnetic fields present, even a weak shear flow causes subtle but coherent correlations in the magnetic fluctuations that oppose zonal flows. The gas in the Jovian interior is magnetized, which explains why the jet streams go as deep as they do, but no deeper. Of course, the polar and subtropical jet streams in Earth's atmosphere help shape the climate, especially at mid-latitudes such as in Australia, Europe and North America. The flows act as kind of barriers, not allowing fluids from either side of the barrier to exchange properties, such as heat, moisture or carbon. Because of this, zonal flows such as Earth's jet streams have a huge impact on the weather and climate, acting as a barrier between hot and cold regions and making it harder for air on either side of them to exchange properties. But the jet streams on Earth are very wavy and irregular. On the other hand, they're much straighter on Jupiter because there aren't any continents or mountains below Jupiter's atmosphere to obstruct the jet stream's path. And so in a way that makes the jet streams on Jupiter simpler and easier to study. Constantino says by studying Jupiter, not only are scientists unravelling the mysteries of the interior of a gas giant, but they can also use Jupiter as a laboratory for studying how atmospheric flows work in general.
These stripes that you see are actually formed because there are very strong winds in the atmosphere of Jupiter that flow all around Jupiter. Very strong winds, alternating winds, a series of winds. So there's a strong wind from west to east, and then above there's another strong wind from east to west, and so on and so on. And in between each of these bands, there's a very strong wind. And these winds are similar to the jet streams we have here on Earth. But unfortunately, the jet streams don't have an imprint on something colorful that we can see if we see a picture of Earth from space. But other than that, they're very similar. Yeah. So that's why we have these bands. Now, people have been studying Jupiter and why these strong winds form in the atmosphere of Jupiter. And there were many theories about how these strong winds form there. And all these theories had various assumptions, and they had various predictions of how deep these winds would continue below the clouds, below the tops of the clouds that we see. And before Juno went there, before NASA spacecraft Juno went up to Jupiter, there was no direct observation to compare with and rule out some of these theories or not. So there was no direct observation of what was actually going on below the clouds. So what happened is that Juno headed out with a mission to approach Jupiter as close as it can get and do precise measurements of both gravity and magnetic fields, and from those infer what goes on beneath the clouds, and try to give us in this way a picture of what goes on beneath these clouds that we see. When the results from Juno came in, it was discovered that these jets, these strong winds, they continue for 3,000 kilometers below the clouds. So they go
deep.
They go deep. They go pretty deep. Not as deep as some of the theories were suggesting. Some of the theories were suggesting that they go all the way down to the interior, but some other theories, for example, were suggesting that they just continue for a few hundred kilometers over a few kilometers. But it was discovered that they go up to 3,000 kilometers, which is pretty deep, and then they stop. So that was discovered in March, and then we had a new puzzle. So why do they stop there, and what goes on there? And here is where me and my collaborator fit in the picture.
One of the things that scientists are intrigued about Jupiter is the possibility that there's a metallic hydrogen mantle above its core, and that would create a lot of magnetism. We've seen Jupiter's aurora activity, and I was just wondering if that could play a role.
Yeah, so yes, it was. So it was it's pretty agreed among the scientific community that, first of all, let's remind ourselves that Jupiter is a gaseous planet. It's all gas. It's all hydrogen and helium mostly. And it's understood that as you go deep inside Jupiter, because the pressure gets so high, then the gas becomes a liquid, and even further down, the pressure is even higher, that electrons pop out of the atoms of helium and hydrogen, and they move around freely, which makes this liquid gas behave as a metal. So that's why we call it liquid metallic hydrogen. And when that happens, then, the movement of the electrons can create currents, and currents create magnetic fields. And this is exactly what you were saying. So this was pretty much understood even before Juno arrived in Jupiter. But what was not really known is what is exactly the structure and the movement of this ocean of liquid metallic hydrogen. And there were some assumptions. Probably there is a solid core deep inside Jupiter or not. Some people were saying yes, there should be. Some people were assuming that there should not be. There shouldn't be any. And Juno's measurements gave us answers for that also. So Juno's discoveries revealed that there is no solid core in the deep interior of Jupiter, but there is indeed this ocean of liquid metallic hydrogen whose movement creates currents and strong magnetic fields.
Does that tell us something about how Jupiter formed? Everyone thought there was this Earth-sized solid core, this seed at the middle.
Yeah, not everybody. Yeah, let's not be too specific.
Right.
But there was a strong consensus on that. Yes, go on. Sorry, if I interrupted you.
All right. So a lot of people thought there was this seed, this Earth-sized terrestrial seed at the center of it all, and it was on this that the planet eventually formed around. And the Juno data shows that's not the case. How surprising was that? What does that tell us about how the planet was formed?
Okay, so to be honest, the planet formation is a bit outside of my expertise, but from what I know, from what I understood, is that was pretty surprising. And this tells us a lot of how the planet formed. I don't know exactly what it tells us, but that was one of the main objectives of Juno mission, by the way, to see what exactly the interior of Jupiter is, so as to understand how exactly Jupiter formed.
And why do we know Jupiter formed? You know how the rest of the solar system formed, because Jupiter contains so much of the solar system's mass.
Exactly. If you take out the sun, 98% of the solar system mass is the sun. But then if you take out that, then more than half is Jupiter. So Jupiter weighs more than all the other planets of our solar system.
What were your findings?
So as we said, the problem was, so after Juno discovered that these jets, these strong winds go as deep as 3,000 kilometers and stop, then there was a question why that happens. Why do they stop there? And also, if you listen to the NASA announcement, you will see that they say, we know now that jets go as deep as 3,000 kilometers. Also, we know that from 3,000 kilometers, more or less, and below, the pressure is so high that the liquid hydrogen becomes contacting and we start having magnetic fields. So 1 + 1 makes 2. Probably magnetic fields have something to do with the jet terminating at that depth, but we don't know. This was the status before our research. So what we did is that we formulated a theory for the interaction of zonal jets, these strong winds, with magnetic fields. And within our theory, we predict that the winds should stop, should shut down when the magnetic field is strong enough. So this comes and probably gives an explanation to Juno's findings, because we know that below 3,000 kilometers, magnetic fields start to be strong, and we know that there are no jets there, there are no strong winds there, and we have a theory now that predicts and explains the mechanism for why is that.
And how did you reach your conclusions?
We were motivated by some computer simulations that were done to understand the interior of stars and gaseous planets. And the simulations were finding that when you have strong enough magnetic fields, the jets turn off, but they couldn't explain why. So we formulated a theory, a mathematical theory, starting out from statistical physics and turbulence theory. From basic principles, we formulated a theory that describes this interaction, and then we plugged in some numbers, and we saw that this theory predicted that as you increase magnetic field strength, then the winds should shut down. And then, after we had this prediction, we looked at the Juno's findings, and we realized that Juno was finding that the strong winds terminate more or less at that point that magnetic fields start to be strong enough. So this gives us credibility for how our theory might be very applicable to explaining what goes on in the interior of Jupiter.
What's your hypothesis as to how a magnetic field affects a jet stream?
So our theory, it's First of all, we had this hypothesis from before, but it also comes out as a prediction of our theory, is that when you have magnetic fluctuations, when you have a turbulent fluid with also magnetic fluctuations in it, that you have that is magnetized and has magnetic fluctuations, then as soon as some strong jet starts forming, it self-organizes the magnetic fluctuations in such a manner so that they coherently act to oppose it and keep it back. So that's why when you have strong enough magnetic fields, you cannot form strong winds. As soon as a strong wind starts to form in one particular place, then the magnetic fluctuations, as if out of a conspiracy, all these fluctuations which seem to be random, they coherently self-organize to align exactly against that.
Almost like a feedback.
It's exactly a negative feedback loop. Yeah.
That's Navid Constantino from the Australian National University. And this is SpaceTime. I'm Stuart Gary. The Earth Explorer Aeolus spacecraft has successfully blasted into orbit on a mission to study the planet's atmospheric wind systems. The 1,360-kilogram spacecraft was launched aboard a Vega rocket from the European Space Agency's Kourou spaceport in French Guiana.
À tous de DDO, attention pour le décompte final. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 1, top. Allumage P80 et décollage VV12 Aeolus.
Rising into the light clouds. All is well on board, says the DDO. Vega weighing 138 tons at liftoff, as she lifts off from French Guiana, beginning the 12th mission in her career. They call her the light launcher at 138 tons, but I guess that's relative. The first stage is burning now. She weighs 97 tons. 88 tons of that are fuel. Most of any launcher's weight is propellant in any system that we're using today. The first stage burns its single engine for about 2 minutes before being jettisoned. First stage is produced in Colleferro near Rome, then delivered to the French Guiana plant here, where it's loaded with fuel and transferred to the booster integration building. You're having returned with a big smile on his face. Before separation is Martin Kaspers. So, how is it?
Incredible.
Tell us.
You see it, you feel it, and all the emotion that comes loose. It's great.
You're laughing.
No, it's not laughter. Yes, it's laughter, but also a cry.
Did you cry? Did you shed a tear?
I did shed a tear.
That's great. What impressed you the most? The sound, the speed, the light, what?
The light was so bright. I had not expected that from such a small launcher. I saw the Galileo or the Ariane launch, but this was much brighter than I had expected.
It's like Times Square out there. You can read a newspaper. P80, first stage separation has come on time. We're into the second stage burn, called second stage the Z23, Z for Zefiro, burns its solid rocket motor for 86 seconds. Avio, of course, responsible for production, integration, and testing of both second and third stages.
Propulsion du Z23, parfaitement nominal.
Vega's launching north, going into a sun-synchronous orbit. Why do we need that sort of an orbit?
We need it for Aeolus, for the instrument, for Aladdin. We want to have a dusk-to-dawn orbit, so that we're always in the sunlight, and it's also the best way to measure the wind profile.
And the orbit is called, they have a name for it, it's ball of yarn orbit, right? Explain that to us.
It is basically you go north to south pole while the Earth is rotating underneath of you, and this way you peel off the Earth completely.
Separation of the second stage. We're waiting for confirmation by the DDO of the third stage, ignition of the third stage.
Allumage
and there you are, right on time. And coming up next, separation of the fairing. All right on time. We can separate the fairing now because we've made it out of the atmosphere.
Aeolus uses laser technology to measure wind speeds around the globe, thereby allowing scientists to better understand the workings of the atmosphere and improve weather forecasting. The spacecraft is named after Aeolus, who in Greek mythology was appointed by the gods as keeper of the winds. The satellite was deployed into a polar orbit 55 minutes after launch, with first contact established through the Troll ground station in Antarctica. The satellite's being controlled from ESA's European Space Operations Centre in Darmstadt, Germany. Mission managers will now spend the next few months carefully checking and calibrating the probe and its systems as part of its commissioning phase. Aeolus uses a completely new laser-based approach to measuring wind speeds from space. It's using Aladdin, the most sophisticated instrument of its kind ever put into orbit. Aladdin is using revolutionary new laser technology to generate pulses of ultraviolet light that are beamed into the atmosphere to profile the world's winds. It's a completely new approach to measuring winds from space. In the process, Aladdin's filling a gap highlighted by the World Meteorological Organization by providing direct global wind measurements. Aeolus will therefore provide scientists with information they need to better understand how wind, pressure, temperature and humidity are all interlinked. The mission will provide an insight into how the wind influences the exchange of heat and moisture between Earth's surface and the atmosphere, important aspects for understanding climate change. You're listening to SpaceTime. I'm Stuart Gary. China has launched 2 remote sensing satellites for Pakistan. The spacecraft were flown aboard a Long March 2C rocket from the Jiuquan Satellite Launch Center in Inner Mongolia's Gobi Desert. The payload included the PRESS-1 optical survey and remote sensing satellite, as well as the PACTES-1A experimental satellite. The 1,200-kilogram PRESS-1 was built for Pakistan by China. It's equipped with 2 panchromatic multispectral imaging cameras with resolutions down to a metre over a 60-kilometre wide area. Although described as being developed to monitor agriculture, urban growth and natural disasters, the probe's also equipped with communications encryption systems. It was placed into a 640-kilometre high orbit, carrying enough fuel for a 7-year lifespan. The second spacecraft in the payload was the 285-kilogram Pakistan Technology Evolution Satellite, or PACTES-1A. Built by Pakistan, it's designed to test locally developed remote sensing technologies from a 610-kilometre high orbit over a 3-year period. The flight was also the 279th launch of the Long March rocket series. A small Japanese spaceflight startup has suffered a spectacular failure, with its launch vehicle exploding to flames just seconds after liftoff. The 10-metre-tall Momo-2 rocket, developed by Interstellar Technologies, was launching from the island of Hokkaido when the disaster happened. Initial reports indicate an engine anomaly just 4 seconds into the flight caused a loss of thrust, resulting in the launch vehicle crashing back to the ground on the launch pad. The single-stage ethanol and liquid oxygen-powered 12-kilonewton rocket was meant to reach an altitude of at least 100 kilometres during this test flight. As it was, the launch had already been postponed since April due to a nitrogen leak. The mission was carrying a scientific payload developed by the Kochi University of Technology to study how sound waves propagate at high altitude. This was the second failure for Interstellar Technologies in 2 launch attempts. Momo-1 crashed and burned back in July 2017, about 70 seconds after launch, when communications were suddenly lost at an altitude of about 20 kilometres, the wreckage falling into the ocean. You're listening to SpaceTime. I'm Stuart Gary. And time now for a brief look at some of the other stories making news in science this week with the Science Report. New research warns that alcohol kills an average of 2.8 million people every year worldwide, and it remains the leading risk factor for premature death and disability in people aged 15 to 49. The findings, reported in the Lancet Medical Journal, suggest that up to 88% of Australian men are drinkers, while the figure for women is 83%. The study also found that alcohol use was linked to 8.4% of premature deaths in Australian men and 2.2% in women. And together that equates to just over 8,000 deaths annually. A new study claims higher levels of carbon dioxide in the atmosphere may threaten human nutrition in many parts of the world. The findings, reported in the journal Nature Climate Change, examine the effects of higher CO2 on iron, protein and zinc levels. The authors found that the increased carbon dioxide levels forecast will cause an additional 175 million people worldwide to become zinc deficient and 122 million people worldwide to become protein deficient by 2050. There are already 1.4 billion women of childbearing age and children under 5 living in countries with over a 20% prevalence of anemia, and these areas are likely to lose 4% of their dietary iron intake. A DNA study of the remains of a 13-year-old girl who died 50,000 years ago shows that she was the child of a Neanderthal mom and a Denisovan dad. The findings, reported in the journal Nature, are based on bone fragments discovered in a Siberian cave. Researchers from the Max Planck Institute found that in addition to a mitochondrial DNA, the girl also inherited 38.6% of her nucleic DNA from a Neanderthal and a further 42.3% of her nucleic DNA from a Denisovan. And it seems her Denisovan dad also had some Neanderthal ancestry, going back between 300 and 600 generations before his birth. It's been revealed that Google is continuing to track its users even when they've turned off their location settings. Despite what they tell you, it seems Google is using Google Maps, weather updates and browser searches to collect location and data on users on a minute-by-minute basis. It seems by turning off location history, users are only stopping Google from adding their movements to its timeline feature. So it looks like the only way you can resolve the issue might be by turning off the web app activity feature, which is enabled by default. Iran has been identified as responsible for a concerted cyber attack targeting scientific research and intellectual property at 33 Australian universities. The findings come as Australia opens a new National Cybersecurity Centre in Canberra. And the new facilities had hit the ground running. It's already dealt with some 14,000 cyber security incidents, costing Australia over $7 billion annually. And globally, the figure's estimated to be around $600 billion. As well as attacks by countries like Iran, North Korea and China targeting defence and national security interests, malicious and criminal attacks remain a primary cause of computer data breaches across Australia. With the details, we're joined by Alex Zaharov-Reutt from IT Wire.
Yes, well, this is information from the Office of the Australian Information Commissioner. Now, in Australia, it was made the law that it was a mandatory data breach regime was put in place, so that if you were a business of a certain size, you had to report if you had a data breach. That's a hack attack, people using whether it's spear phishing or brute force attacks or some other method to guess people's passwords and then to breach databases and suck that information out and put it on the dark web. Well, in Australia, there were 242 data breaches in the last 3 months. And that's startling. I mean, it's incredible because, we didn't hear about these things before. We heard about the big Sony hacks and other hacks overseas, Equifax and those other sort of organizations with millions, if not tens or hundreds of millions of US subscribers. But these hack attacks are happening around the world. And unless the company reports it and you know about it, how do you know to change your password or to take whatever action you need to take to secure your information? I mean, obviously, it's of paramount importance to not use the same password on various different sites.
It's not just the information you're keeping, but also the information companies are keeping or the government are keeping on you. Right now, for example, here in Australia, the My Health Record electronic data scheme is all the go. It's what everyone's talking about. And there are some very legitimate concerns as to whether or not the federal government can actually hold those medical records secure.
Absolutely. The government talks about military-grade security, but what about all of the other providers, the doctors and hospitals and other places that can access that information? What about attacks through their networks? And what about the fact that, governments have been hacked as well? I mean, just because the government says it has military-grade security doesn't mean that very smart and advanced hackers can, target the weakest link, which is people, to try and get credentials and break into systems and then, again, sell that information on the dark web. And look, if there's information about you, about your health status, about diseases you might have had or problems you've had, some of that information can come in to be used for blackmail or all sorts of different scenarios. So, yeah, there's obviously a great deal of concern about databases and, who is securing those. Sadly, it's at risk, and doesn't matter how strong the good guys seem to make their systems, the bad guys always seem to find a way to get around it.
And that report by Alex Zaharov-Reutt from IT Wire. You're listening to Space Time. I'm Stuart Gary, and that's the show for now. You can subscribe and download Space Time as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from spacetimewithstuartgary.com, or from your favorite podcast download provider. SpaceTime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., and available around the world on TuneIn Radio. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at Spacetime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. This has been another quality podcast production from Bytes.com.